Champions present
The Supercharged World of Chemistry, Part 3. Starring...
Hey, we're here to, not get chemistry. Is someone cooking eggs? Oh.
The magnetic quantum number, or M sub L, describes the orientation of the orbital in space.
You are the most boring element ever.
Ow.
I'm gonna go kill some rats! Red rum! Red rum!
The traffic around here, it's just too much! Ah!
Bonjour, ma chérie.
And for just $19.99, you can get this wonderful diamond ring.
Also starring Chaz Maston and Christiana Celeste.
How did I, Helium Man, end up with so many bad elements?
Pat, I'd like to buy a vowel. I'd like to buy an A, an E, an I, an O.
Hi, I'm Gabrielle Smith. Welcome to the Supercharged World of Chemistry Part 3. We're darn glad you're here. Get ready to top off that little test tube in your head with more of our chem-filled solution, including full sections on molecular geometry, bonding theories, gases, states of matter, properties of solutions, and much more.
As always, don't forget to pause, stop, or rewind this video cassette at any time you like.
Hey kids, also, just because this is standard policy, we need to remind you that to truly learn chemistry, you need to attend your classes, read your books, and listen to your professors.
Part 1, Molecular Geometry and Bonding Theories.
No, molecular geometry.
Molecules come in a variety of different shapes. Molecular geometry is the geometric arrangement of the atoms in molecules and in covalently bonded crystals. When you see those funky models of strange molecules that look like kids' building toys, those are there to help you understand molecular geometry.
The two types of bonds, ionic bonds and covalent bonds, form different structures. Ions attract as many ions of opposite charge as they can pack around them. Covalent bonds are a little different. Two covalently bonded atoms share a pair of electrons, and the bond is called a directional bond, since the arrangement of covalently bonded atoms is more neat and specific. They are not just all crammed together.
Section A, the VSEPR theory.
Scientists have developed a number of theories about how atoms arrange themselves in a molecule. The shape the atoms form in a molecule is called molecular geometry. A common model used to predict molecular geometry is the valence shell electron pair repulsion model, known as the VSEPR model. The VSEPR model predicts molecular geometry by describing how electron pairs bond and theorizing how electron pairs and bonds will affect the shape of the molecule. According to the VSEPR model, the electron pairs in a molecule's valence shell are arranged so that they're as far away from each other as possible. In other words, the electrons act like they repel each other.
Whenever you're trying to predict molecular geometry, be sure to VESPER.
The VSEPR model says that a molecule with two pairs of shared electrons has a linear shape. Using the VSEPR theory, if you know that a molecule has two pairs of shared electrons, you can predict that the molecule will have a linear shape. This linear-shaped molecule is represented by the notation AX sub 2. The sub 2 tells you that there are two pairs of shared electrons.
AX sub 2.
Linear!
A molecule with three pairs of shared electrons is called trigonal. And here's a picture of what the VSEPR theory says it looks like. Trigonal molecules, those that have three pairs of shared electrons, are represented by the notation AX sub 3. The sub 3 tells you that the molecule has 3 pairs of shared electrons.
Molecules can also have non-bonding electron pairs. The non-bonding electron pair takes the place that a regular bond would occupy. We will use water again as an example, but know that this example shows you only one of the many possible arrangements of bonds and atoms. Be sure to check out the others in your textbook.
I'm checking out the other arrangements in my textbook.
Water has 2 bonds between hydrogen and oxygen, but oxygen also has 2 non-bonding electron pairs. This gives water a tetrahedral arrangement of electron pairs and bonds. Since diagrams don't usually show the non-bonding electrons of oxygen, we usually just say that the water molecule is bent, rather than referring to it as tetrahedral.
That, bent, bent, bent.
The geometric arrangement of the bonds in a molecule, along with the electronegativities of the atoms, or how strongly some of the atoms hog the shared electrons, determine the molecule's polarity.
As we mentioned before, a molecule made of 2 different atoms with different electronegativities is held together with polar covalent bonds. The atom with greater electronegativity is a bigger electron hog, so it creates a slightly negative charge for itself and a slight positive charge for the atom it's supposed to be sharing electrons with. This arrangement forms what we call a dipole. Dipole molecules have slightly positive and slightly negative regions on them, but they are still considered neutral molecules. The small charges on regions of the molecule just affect the way a group of these molecules would line up alongside each other. Dipole molecules tend to line up so that the negative part of one molecule pairs with the positive part of the next. These attractions between polar molecules are known as dipole-dipole forces. We'll talk more about dipole-dipole forces later.
Dipole!
Dipole!
So you don't need a protractor to figure out molecular geometry. The VS-EPR theory predicts the shape of molecules based on their bonds. If you remember in the Part 2 orbital section, we said that you need to know where the electrons are in the molecules. Now you know why. The position of electrons affects the shape and behavior of molecules. This is certainly true with polar molecules, which have an electronegative atom that hogs the electrons and gives itself a slightly negative charge, and the atoms around it slightly positive charges. Water molecules, for example, stick together because they are polar. It all comes back to the placement of those electrons.
Section B. Orbital overlap.
There are 2 accepted theories about how atoms bond together to form a molecule. They are called hybrid orbital theory and molecular orbital theory. The 2 theories try to explain pretty much the same thing, how molecules hold together, but each explanation is just a little different. We'll tell you about hybrid orbitals first.
So you understand a bit about orbitals, how an atom's electrons move around its nucleus, right? Well, when molecules form, the orbitals of the component atoms overlap with each other to form hybrid orbitals, mixtures of the overlapping atomic orbitals. These overlapping, or hybrid orbitals, let 2 electrons with opposite spins come together to form a covalent bond that helps hold the molecule together. Hybrid orbitals, like atomic orbitals, can only hold 2 electrons each. So mixing 2 atomic orbitals creates 2 hybrid orbitals.
A molecule's Lewis structure shows you how many hybrid orbitals the molecule will need in order to accommodate all its bonds and unbonded electron pairs. Some combination of the atom's outer or valence orbitals will combine to form the hybrid orbitals.
In 1910, farmer Otis Springwald, whose favorite foods were beef and chicken, experimented with combining beef and poultry. After 17 years of hard work, he introduced the cow chicken.
So, you need a hybrid orbital for each bonded and unbonded pair of electrons in a molecule. For example, here's the Lewis structure for beryllium hydride. Beryllium is the central atom and the hydrogens are bonded to it. According to the Lewis structure, there are 2 bonds that need to be accommodated by hybrid orbitals, so there will be 2 hybrid orbitals.
Now let's look at the orbital diagram for beryllium. Beryllium's electrons fill up one s and 2 s orbitals. Here's hydrogen's orbital diagram. It only has a single electron in the 1s orbital, So we have two hydrogens, each with a single electron in its 1s orbital. Now we want to set this up so each of hydrogen electrons can bond with one of beryllium's electrons, and each bonded pair gets a hybrid orbital of its own.
There's a real neat trick we can do to arrange beryllium's electrons in such a way that they can bond with hydrogen's electrons. We can promote an electron from the 2s orbital to the 2p orbital, and now beryllium's orbital diagram looks like this. Now there is only one electron in the 2s orbital and one electron in the 2p orbital. Beryllium's s and p orbitals mix to form two sp hybrid orbitals. These sp hybrid orbitals can bond with hydrogen's orbitals.
These hybrid orbitals will always arrange themselves as far from each other as possible. And in this case, the orbitals are 180 degrees from each other.
You just stay over there on your side.
Conveniently, there's an easy way to figure out how many hybrid orbitals will form in a molecule.
A molecule's hybrid orbital number will tell you how many hybrid orbitals the molecule needs. The hybrid orbital number is the number of bonds and unbonded electron pairs that form around the atom in the center of the molecule. When you count bonds for hybrid orbital numbers, double and triple bonds count as a single bond. This chart will tell you how the orbitals will hybridize based on the hybrid orbital number. Yippee!
Yippee! Yippee!
Now let's decide how the hybrid orbitals will form around boron in the compound boron trifluoride, BF3. We'll start by looking at the Lewis structure for BF3. Count the number of single bonds and the lone electron pairs around boron, the atom in the center. We see 3 single bonds and no lone pairs, so the hybrid orbital number is 3. Now look at the chart. To accommodate the 3 bonds, we need 3 sp squared hybrid orbitals.
3 bonds. 3 hybrid orbitals.
BF3's 3 bonds form a trigonal planar arrangement.
Methane, CH4, forms a 3-dimensional molecule. You can tell by the Lewis structure that methane has 4 single bonds. Check the handy chart and you'll see that 4 bonds gives methane a hybrid orbital number of 4 and a 3-dimensional tetrahedral arrangement.
Now on to molecular orbitals. Molecular orbital theory is another model that explains how molecules hang together. The orbitals from the atoms in the molecule overlap to form covalent bonds that glue the atoms together. When 2 atomic orbitals overlap, they form 2 molecular orbitals. Let's look at hydrogen, for example.
The 2 overlapping 1s hydrogen orbitals form 2 molecular orbitals, one with high energy and one with low energy. The low energy bonding molecular orbital forms the covalent bond that holds the nuclei together. The friendly bonding electrons in the bonding molecular orbital crowd between the 2 hydrogen nuclei and join in the covalent bond that holds the atoms together. The high-energy anti-bonding molecular orbital doesn't help hold the molecule together. This orbital not only has fewer electrons, but the high energy and bad attitudes of the anti-bonding electrons keep them from bonding with each other. Each molecular orbital can hold 2 electrons with opposite spins, just like atomic orbitals.
In the molecular orbital theory, the term bond order refers to another way of counting bonds between 2 atoms and a molecule. More bonds make a more stable molecule, so a high bond order number indicates a molecule that'll hold together pretty well. To find bond order, subtract the number of antibonding electrons in the molecular orbital from the number of bonding electrons. Then divide that number in half. Now you divide it in half because you're counting the number of pairs, not the number of single electrons.
Calculating bond order is pretty easy. Let's go back to the hydrogen example. Hydrogen has 2 bonding electrons and 0 anti-bonding electrons. So the equation we'll use to find hydrogen's bond order looks like this. 1/2 of the quantity, 2 minus 0, equals 1. The bond order for hydrogen is 1.
Hold it. How do I know how many bonding electrons and how many anti-bonding electrons there are?
Glad you asked.
It's not too hard actually. Remember that each orbital can only hold 2 electrons, and electrons will always go to the lowest energy orbital first. So, count up the number of electrons you need to accommodate. Let's say the molecule has 5 electrons. 2 will go to the first bonding molecular orbital, the next 2 will go to the first antibonding molecular orbital, and the 5th will go to the second bonding molecular orbital. So, there are a total of 3 bonding electrons and 2 antibonding electrons. Say your molecule has a total of 8 electrons to accommodate. 2 will go to the first bonding molecular orbital, 2 will go to the first antibonding molecular orbital, 2 will go to the second bonding molecular orbital, and 2 will go to the second antibonding molecular orbital. So, in this case, you have 4 bonding electrons and 4 antibonding electrons.
So, there are 2 models that explain how molecules hold together: the hybrid orbital theory and the molecular orbital theory. Hybrid orbital theory says that when the orbitals of 2 atoms in a molecule overlap, they form a covalent bond that holds the molecule together. The number of orbitals that overlap depend on how many need to overlap to accommodate all the pairs of bonded and unbonded electrons. Molecular orbital theory says that when 2 orbitals come together, one from one atom and one from another, 2 new orbitals will be formed, one with low energy and one with high energy. The low energy or bonding molecular orbital forms a covalent bond that holds the molecule together. The high energy or anti-bonding molecular orbital does not help hold the molecule together at all.
Part 2. Gases.
You know lots about gases. Take a deep breath. Go ahead. You just sucked up a bunch of gaseous molecules! Not to mention a few dust mites. Elements that make up the air you breathe, like nitrogen and oxygen, are gases under ordinary conditions, or the normal conditions of the Earth's climate. Some substances, like water, can be in a liquid, solid, or gaseous state under ordinary conditions. For instance, if you have a closed container of ice water, there is ice, the solid, water, the liquid, and water vapor, which is the gas formed by evaporating water. So it's got all 3!
Gases act differently than solids or liquids. For one thing, they expand and compress real easily. If you put a little gas in a container, like my helium tank, the gaseous atoms, or molecules, will move away from each other to fill up the whole container. If you want to, you can put a lot of gas in this tank because the gaseous atoms, or molecules, will pack real close together to allow more atoms in.
And that's a good thing, because often I like to suck helium out of my tank.
We describe gases based on these 4 properties: mass, volume, pressure, and temperature. We'll use grams and kilograms to measure the mass, and liters and milliliters for volume.
The pressure of a gas is the force it exerts on a unit of area. In other words, when we measure the pressure of a gas, we're measuring how hard the gas is pushing on the stuff around it. Atmospheric pressure is the force exerted by the atmosphere on a unit of the Earth's surface. As we said before, the unit used to measure pressure is the atmosphere. So don't confuse the unit, atmosphere, with the term atmospheric pressure.
Kelvin is the temperature unit you need for gas equations. When you're talking about temperature on the Kelvin scale, don't refer to it as degrees Kelvin. The units are not degrees. They're simply called kelvins. Your professor might ask you to calculate a problem involving gases and give you the temperature in degrees Celsius. Don't fall for that old trick. Just convert to kelvins. It's real easy. You just add 273.15 to the Celsius reading. So, 0 degrees Celsius equals 273.15 kelvins. 22 degrees Celsius equals 295.15 kelvins, and so on. You get the picture.
Do you like chemistry? Yeah. Did you know your pants were unbuttoned? Yeah. How about when you have help, like from a video course review that uses humor to spice up the material? Yeah, it gets easier. Yeah.
Celsius to kelvins at 273.15.
Now to kinetic molecular theory. Red rum! Red rum! Red rum!
Section A, Kinetic Molecular Theory.
So gases act differently than solids or liquids. Kinetic molecular theory explains why gases act the way they do.
All these theories. Can't chemists ever just say anything for sure?
You could say one thing for certain. You are getting on our nerves.
The kinetic molecular theory is based on these 5 assumptions.
Number 1. A gas is composed of molecules that are far apart from each other in comparison with their own dimensions. So most of the volume a gas occupies is really empty space.
I'm just a gas in space!
2. Gas molecules are in constant random motion. Each molecule continues to move in a straight line unless it collides with another molecule or with a wall of the container.
3. The molecules exert no force on each other or the container until they collide with each other or with the walls of the container. So, if a gas molecule is just cruising around in space, minding its own business and not running into anything, it's not exerting any force on its fellow molecules or the container.
Hey, I'm just cruising. I'm not bothering anybody.
Oh yeah, till you ran into me, you idiot!
The average kinetic energy of the molecules of a gas is proportional to the temperature. This one sounds complex, but think about it this way. When you heat up a pot of water, the molecules start moving really fast. Then they escape from the pot, or boil off. The movement of the molecules is the kinetic energy. As the temperature goes up, the molecules move faster. The more heat there is, the faster the molecules move. So, the kinetic energy is proportional to the temperature.
And number 5, every time a molecule collides with the wall, it exerts a force on it.
Uh-oh, we do that.
And here's an effect of this rule number 5. If you decrease the volume of a container of gases, in other words, if you make the container smaller, the number of molecules per unit of volume increases. So, if you put the same amount of gas in half the volume, the pressure of the gas doubles as a result of increasing collisions with the wall. This phenomenon is called Boyle's law.
Half the size, twice the pressure. Boyle's law.
Now let's go over diffusion and effusion, 2 important properties of gases.
Gases can also diffuse and effuse. Diffusion is the process by which one gas mixes with another.
Effusion is the process by which a gas escapes from a container through a very small hole, like if you open a helium-filled balloon and let the helium escape. The helium gas diffuses into the air, and once the molecules escape through effusion, we can say they feel, well, effusive.
The rate of diffusion, or effusion of a gas, is inversely proportional to the square root of its molar mass. What the heck does this mean? Well, simply this. The heavier a gas is, the slower it diffuses or effuses. This phenomena is called Graham's law.
Not only am I a snack food, but I made a law. Once again, my law states the heavier a gas is, the slower it effuses or diffuses.
Section B, the ideal gas equation.
Chemists, wacky idealist dreamers that they are, came up with an equation to describe how gases ought to behave. It is called ideal gas equation, and it is useful because it shows us the pressure, volume, and temperature, as well as the moles of any hypothetical gas. We use this equation constantly to describe and understand the behavior of gases. Of course, the equation is hypothetical, since in real life, there are always factors that throw a monkey wrench into the works and skew the numbers. But hey, that's why it's called ideal. You can remember the equation, PV equals nRT, because it looks kind of like pervnert.
In the ideal gas equation, P represents the pressure of the gas, V equals the volume, N equals the number of moles we're working with, and R is the gas constant, and T is the temperature. R, the gas constant, is one of those deals you can just look up in your book. It's 8.314 joules per mole times Kelvin, or 0.0821 atmospheres times liters per moles times Kelvin. Either one works in the equation. You can choose which form of the gas constant you use, depending on whether you need to work with joules, a unit that measures energy, or atmospheres, a unit that measures pressure. So the gas constant doesn't change, and that's why it's called a constant. You can use the ideal gas equation to find the partial pressure of a gas.
The partial pressure of a gas in a mixture is the pressure exerted by one of the gases in the mixture. Dalton's law of partial pressures says that in a mixture of gases, the total pressure exerted is the sum of the pressures that each gas would exert if it were present alone under the same conditions. So the total pressure equals the pressure of the first gas plus the pressure of the second gas plus the pressure of the third, and so on. So you would use the Perv-Nernst ideal gas law to find the pressure of each gas and then use Dalton's partial pressure law to find the total.
Here's an example. Suppose we have a 1-liter flask containing 5 grams of carbon dioxide and 2 grams of oxygen molecules, and the temperature is 25 degrees Celsius. We have to find the partial pressures of each of the gases and the total pressure in the flask. We can use the ideal gas equation, Perv-Nernst, but first we have to rearrange it so it's more useful to us. We'll set up the equation so it finds the pressure P, which is what we're looking for. Use some algebra to rearrange the problem.
Algebra?
It's not that bad. Just divide the whole deal by the volume. So the equation now looks like this. Pressure equals the quantity of the number of moles times the gas constant times the temperature divided by the volume.
Pressure? Don't tell me about pressure. I feel pressure from above, pressure from below.
Let's start by converting our temperature from degrees Celsius to kelvins. That's really easy. Just add 273.15 to the degrees Celsius, and we get 298.15 kelvins.
Remember, to go from Celsius to kelvins, just add 273.15.
Now we have to determine how many moles of each gas are in the flask.
If you watched the Supercharged World of Chemistry Parts 1 and 2, I bet you could teach your dog how to convert from grams to moles, but we'll go through it again anyway.
This is the equation we'll use for the conversion. N, the number of moles, equals 1 mole of your substance over the weight of 1 mole of your substance in grams times the mass of your sample.
And here's a quick reminder about finding the weight of your substance in grams per mole. If your substance consists of a single type of atom, you can look up the mass of that atom in AMUs in the periodic table. Then, since 1 mole of any type of atom has a mass in grams equal to the atom's atomic mass measured in AMUs, you can literally just change your units from AMUs to grams per mole. The mass in grams of a compound that's made up of crystals, like NaCl, is called the formula weight. The formula weight is just the sum of the masses of the atoms in the compound's empirical formula. The mass in grams per mole of a substance that consists of molecules is called molecular weight. To find molecular weight, take the mass of each of the molecule's component atoms in AMUs and add them up. So for instance, to find the mass in grams per mole of the oxygen molecule in our pressure example, just find the mass of oxygen, multiply it by 2, and slap the unit grams per mole on the end. So here we go, converting our sample of oxygen from grams to moles so we can find its partial pressure in the flask. N, the number of moles of oxygen molecules, equals 1 mole of O2 over the weight of 1 mole of O2 in grams, 32 grams, times our sample, 2 grams of O2. Multiplying our sample, 2 grams, by 1 mole of O2 over the mass in grams of a mole of O2 is like multiplying by 1. So it changes units without changing amounts. See, if you weighed out 1 mole of oxygen molecules, it would weigh 32 grams. So in effect, 1 mole of O2 and 32 grams of O2 are the same thing. That's why it's like multiplying by 1. 1 mole of O2 over 32 grams of O2 multiplied by our 2 gram sample gives us 0.0625 moles of oxygen molecules.
Remember, the ideal gas law, PERV-NERT, is rearranged to solve for pressure. Pressure equals the quantity of the number of moles times the gas constant times the temperature divided by the volume.
Now let's plug the numbers into our equation to find the pressure of the oxygen in the flask. The pressure equals the quantity 0.0625 moles times the gas constant. Now you need to choose one of the two gas constants. Since we want pressure, and since the total flask is measured in liters, use the one in atmospheres and liters. That's 0.0821 liters times atmospheres per moles times Kelvin. Those two quantities are multiplied by the temperature, which we determined was 298.15 kelvins. And all that is divided by the volume, 1 liter. Now here comes a little more algebra.
Relax, it's not hard.
The denominator in the gas constant, moles times Kelvin, shifts down to the denominator of our equation. So we'll cross out all of the terms in the equation and multiply the terms in the numerator. That leaves us with 1.53 atmospheres, the pressure of the oxygen in the flask.
On to carbon dioxide. We have to convert from grams to moles again. The number of moles of carbon dioxide equals 1 mole of carbon dioxide over the molecular weight of 1 mole of carbon dioxide, 44 grams, times the weight of our sample, 5 grams. That equals 0.114 moles.
Now we're ready to find the pressure of the carbon dioxide in the flask. The pressure, P, equals the quantity of 0.114 moles times the gas constant, 0.0821 liters, times atmospheres per moles times Kelvin, times the temperature, 298.15, all divided by 1 liter. Again, we'll move the denominator of the gas constant to the denominator of the equation and cancel out the units. That gives us 2.79 atmospheres, the pressure of the carbon dioxide in the flask.
Finally, to find out the total pressure in the flask, just add up the individual partial pressures. 1.53 atmospheres plus 2.79 atmospheres equals 4.32 atmospheres. So the total pressure is 4.32 atmospheres.
But now, a bit more about moles. There is a simplified version of the equation to convert grams to moles that your esteemed chemistry professor will probably expect you to know. It's really quite simple.
This is very important, humans.
Here's the equation you've been using to convert from grams to moles. Like we said, it uses the unit factor method to change units from grams to moles by multiplying the weight of your sample by 1 mole of the sample over the molecular or formula weight of the sample in grams per mole.
Grams to moles. Grams to moles.
Now here's the simplified version. You can just ignore the 1 mole of substance in the numerator because it doesn't do anything for the values in your equation. Just take a shortcut and put the mass of your sample right over the molecular or formula weight in grams per mole of your substance and calculate it that way.
So for instance, this is how we converted carbon dioxide from grams to moles in the pressure calculation we just did. Let's do it again using the simplified version of the equation.
We'll put the mass of the sample of carbon dioxide, 5.00 grams, over the molecular weight of carbon dioxide, 44.0 grams per mole. So cancel out the grams and divide 5.00 grams by 44.0 grams per mole, and you get the same answer you got before, 0.114 moles.
Enough about the moles already. Get back to the gases.
When you work with the ideal gas laws, keep in mind that there will be deviations from ideal behavior.
I think maybe you could rip your shirt off for me?
Yeah, I guess so.
Yeah.
real life, gases don't obey the law. Two excuses the gases have for not obeying the ideal gas law are: one, when the molecules are crammed into a very small space and the pressure is high, the molecules take up a significant fraction of the empty space, and this can skew your results. And two, there are intermolecular forces acting between the molecules. Now, what the heck are intermolecular forces? Stay tuned!
So, the ideal gas equation describes the pressure, volume, and temperature of any hypothetical gas. You can rearrange the ideal gas equation to find the partial pressures of gases in a container. Then, if you add up the partial pressures, you get the total pressure of the gases in the container. It's important to remember that the ideal gas equation describes hypothetical gases that behave exactly like they're supposed to. In real life, gases just don't always behave like the ideal gas equation says they should.
Part 3. States of Matter. Section A. Intermolecular Forces.
Intermolecular forces are the forces of attraction between molecules. They are not as strong as ionic and covalent bonds, but they definitely have an effect on states of matter. The intermolecular forces operating on gas molecules are not that strong, and they allow gas molecules to move away from each other. The intermolecular forces between molecules in a liquid are a bit stronger, so liquids hold together and assume the shape of whatever container you put them in. Solids have strong intermolecular forces at work between the molecules, locking the molecules in place.
Intermolecular forces are responsible for the condensation of gas molecules into their liquid state. Gas molecules normally move pretty fast, but as the temperature decreases, the speed, or kinetic energies, of the molecules also decrease. As gas molecules slow down, they begin sticking together, and when they finally do stick together, they form a liquid. This change of state from gas to liquid is a result of intermolecular forces, the forces that made the molecules stick together.
Intermolecular forces! Intermolecular forces!
In the liquid state, the molecules still have some kinetic energy, although the liquid is more dense than a gas. As the temperature continues to fall, the molecules lose more of their kinetic energy. With less kinetic energy, the molecules slow down, and the attractive forces between them cause them to congregate and solidify. Here comes another change of state. Presto, we have a solid.
There are 4 types of intermolecular forces, all with funny names. They are ion-dipole interactions, dipole-dipole interactions, London dispersion forces, and hydrogen bonds.
Ion-dipole interactions exist when a solid substance made of ions is dissolved in a liquid consisting of polar molecules. For example, when sodium chloride, an ionic solid, is dissolved in water, a polar liquid, the solid salt crystals break up and form the ions, Na positive and Cl negative. The positive charge on the polar molecule moves towards the negative ion of the salt, and vice versa.
The term dipole is just another word for polar molecule. Dipole-dipole forces result from the slight charges on the ends of polar molecules, causing them to stick together. It's the dipole-dipole forces between water molecules that cause bodies of water to have surface tension. These forces are relatively weak because the charges on polar molecules are pretty small. But even the small polar charges are enough to create a tangible force. And when you do a belly flop into the pool, ouch! You definitely notice the dipole-dipole forces between the water molecules. The polar molecules try to hold together.
London dispersion forces are intermolecular forces that result from fluctuating instantaneous dipoles. I'll explain in English. You can't have dipole-dipole forces between nonpolar atoms and molecules, right? Because there are no charges attracting the molecules to each other. But a guy named Fritz London... Who? Fritz London! He figured that since nonpolar molecules can become liquid, there must be some intermolecular force at work between nonpolar molecules. So he came up with this idea of instantaneous dipole movement.
Fritz London figured that even nonpolar atoms like helium might sometimes have both their electrons on one side of the nucleus for just an instant. Old Fritz called this coincidence instantaneous dipole movement. For just an instant, a normally nonpolar atom or molecule is polar. Then, of course, the electrons move and the atom or molecule isn't polar anymore. But when one atom becomes polar for an instant, the force of its electrons on one side repels the electrons on the atom that's next to it, making that one polar for a moment by shoving both of the atom's electrons to one side. This can continue in a kind of domino effect until a whole bunch of atoms are polar for an instant. When this happens, you get a real quick and temporary dipole-dipole type attraction between normally nonpolar particles. London dispersion forces operate between polar molecules too, increasing the attraction between the polar molecules.
We're here in London. The dispersion forces have begun the bombing, pushing our electrons to one side, which makes us polar for just an instant.
Hydrogen bonds are intermolecular forces too. And guess what? They deal only with hydrogen. When a hydrogen atom bonds to a strong electronegative atom, it forms a polar bond. The electronegative atom pulls hydrogen's electrons toward itself. The hydrogen, with its electron pulled away from it, has a tiny positive charge. It is then attracted to an unshared electron on another atom. This attraction, found in molecules like water and hydrogen fluoride, is the last type of intermolecular force.
So, intermolecular forces are the forces of attraction between molecules. Ion dipole forces, dipole-dipole forces, London dispersion forces, and hydrogen bonds all make molecules stick together. Intermolecular forces can cause gas molecules to stick together to become a liquid, and, in the case of solids, they can lock molecules rigidly in place.
Section B. Phase diagrams.
A phase change is the transformation of a substance from one state to another. When ice melts, the substance water is changing from its solid phase to its liquid phase. Now, as water boils, it goes from its liquid phase to vapor, its gaseous phase.
A phase diagram shows us what phase a substance is in at particular temperatures and pressures. At low temperature and high pressure, a substance is generally in its solid phase. At high temperature and high pressure, the substance is generally a liquid. And at high temperature and low pressure, the substance is usually a gas. When two opposing processes are occurring at the same time, for example, if a liquid is evaporating and condensing simultaneously at the same rate, it is called equilibrium. The lines on the diagram represent the equilibrium point between states. The intersection of the three lines on the diagram is called the triple point. This point represents the pressure and temperature at which all three phases are at equilibrium. In other words, at the specific pressure and temperature indicated by the triple point, a substance moves between its liquid, gas, and solid phases simultaneously and at the same rate. So, a phase diagram gives us a nice graphical summary of the phases of a substance.
Section C. Vapor pressure.
Vapor pressure is the constant force that vapor exerts above a liquid when equilibrium is established in a closed system. That means that when you put some liquid in a jar and put a lid on it, with the appropriate temperature and pressure, the liquid will start turning to vapor inside the jar. After a while, the vapor will begin condensing again, and the system will reach equilibrium between the liquid and vapor phases. In other words, the substance will be condensing into a liquid and evaporating into gas at the same time and at the same rate inside the jar. Once equilibrium is established inside the jar, we can measure the vapor pressure.
Vapor pressure is the force of the vapor pushing down on the water inside the jar. How strong the vapor pressure is depends on how many molecules can escape into the gas phase. More gas molecules means higher vapor pressure. And how many molecules can become gas depends on the temperature and the strength of the intermolecular forces that hold them together. For example, the hydrogen bonds that hold water molecules together are pretty strong, so water molecules don't escape into vapor phase very easily. Gasoline, on the other hand, has much weaker forces holding its molecules together. You can tell that gasoline vaporizes easily because you can smell gas vapor when you fill your tank.
Okay, so I think I got it. Intermolecular forces like ion dipole forces, dipole-dipole forces, London dispersion forces, and hydrogen bonds help molecules stick to each other. Intermolecular forces have an effect on phase changes, like they can cause a gas to turn into a liquid, right? When the gas molecules start sticking together. Substances change phases at specified temperatures and pressures, and when a substance is changing back and forth from one phase to another simultaneously and at the same rates, we say the substance is at equilibrium. Cool, man.
Part 4. Properties of solutions.
We're back to solvents, solutes, and solutions. Just like in the supercharged world of chemistry part 1. And just in case you didn't buy it, here's a recap of the terms you'll use with solutions.
A homogeneous mixture of substances with the same physical and chemical properties throughout it is called a solution. In the solution, the substance present in the largest amount is referred to as the solvent, and the other substances are the solutes. If one component of a solution is a solid, the solid is always the solute.
Section A. Solution formation.
Not all liquids can combine to make a solution. Liquids that can dissolve in each other are called miscible. Liquids that are insoluble in each other are called immiscible. The general rule for solutions is like dissolves like. Ionic and polar solutes are soluble in polar solvents. For instance, the ionic solid NaCl, or table salt, can dissolve in water, a polar liquid. And non-polar solutes are soluble only in non-polar solvents. For instance, cooking oil is a non-polar substance. You know, you can't dissolve cooking oil in water, right? Right. That's because water is a polar solvent. You have to dissolve a non-polar substance like oil in a non-polar solvent like carbon tetrachloride.
Like dissolves like.
The solubility of a substance is the maximum amount of that substance that can dissolve in a particular solvent at a particular temperature. Solubility varies depending on the temperature of the solution, the temperature of the solvent, and if the solute is in its gas phase, then its solubility also depends on pressure.
For instance, there's only so much salt that will dissolve in a glass of water. If you keep adding salt to the water after you hit that saturation point, the salt won't dissolve. It'll just lie in the bottom of the glass. If you change the temperature of the water or of the salt, the saturation point will change. So if you raise the temperature of the water, you can dissolve more salt in it. If you lower the temperature, you will usually reach the saturation point sooner.
Solubility refers to how much of a solute can be dissolved into a solvent.
A saturated solution is a solution at equilibrium with a solvent that has accepted the maximum amount of a solute that it can. So solubility refers to the maximum amount of solute that you can dissolve in a solution. The term saturated solution refers to the solution itself after the maximum amount of a solute has dissolved into it.
A saturated solution has accepted all the solute it possibly can. No mas! No mas!
If the proportion of solute is large, the solution is considered concentrated. A dilute solution has a small amount of solute compared to the amount of solvent.
Solutions in water are called aqueous solutions, and the solutions with a high concentration of ions have greater electrical conductivity than solutions with neutral molecules. Solutes that form conductive solutions are called electrolytes.
A strong electrolyte, like sodium chloride, ionizes completely in an aqueous solution, and the ions make the solution conductive. Electricity is moving well through this concentrated sodium chloride solution, so the light bulb can burn brightly. Acetic acid, or vinegar, is a weak electrolyte because it does not ionize completely in an aqueous or water-based solution. Only some of the solute is ionic, and the solution is less conductive. The electricity does not move through the weak electrolyte as well, so the light bulb does not burn as brightly.
Section B, concentration.
When we refer to the composition of a solution, we're talking about not only what components make up the solution, but also the concentrations and ratios of the components in the solution. There are several ways of expressing the composition of a solution: mass percent, mole fraction, molarity, and molality. And you'll have to know how to find them all.
First, mass percentage composition.
The mass percentage composition of a solution measures the number of grams of solute in each 100 grams of solution. Mass percentage equals the mass of the solute divided by the mass of the whole solution times 100, of course, for percent. The mass of the whole solution equals the mass of the solvent plus the mass of the solute.
So, to find the mass percentage composition of a solution containing 10 grams of NaCl, or table salt, in 90.0 grams of water, we first find the mass of our solution. That's easy. 10 grams of salt plus 90 grams of water equals 100 grams. Now we use the percentage composition formula. The percentage composition of salt in the solution equals the quantity 10 grams divided by 100 grams times 100. And that equals 10%.
Hey, what's the mass percentage of my big toe in this coffee mug?
Shut up!
The mole fraction of a compound, also known as X, is equal to the number of moles of the compound you're measuring divided by the total number of moles of all components of the system. The mole fraction is kind of like percent composition because it tells you in moles what part of the whole solution the component you're measuring is. When you add up all the mole fractions in a system, your answer will always equal 1.
Here's an example of how to find the mole fraction. We'll go back to the example we just did, with 10 grams of sodium chloride in 90 grams of water. To find the mole fraction of NaCl, or salt, in the solution, we first have to convert from grams to moles, of course, because mole fractions are measured in moles. We'll convert from grams to moles using the simplified version of the conversion equation we talked about earlier. That's the mass of the sample, 10.0 grams, over the formula weight of NaCl. Now remember, we use formula weight for NaCl because it is a crystal, not a molecule. The formula weight of 1 mole of NaCl is the sum of the masses of the atoms in NaCl's empirical formula. The mass of sodium, 23.0 grams per mole, plus the mass of chlorine, 35.5 grams per mole, equals 58.5 grams per mole. So, 10.0 grams divided by 58.5 grams equals 0.171 moles.
Now we'll do the same thing to find out how many moles of water we have. Our sample, 90.0 grams, divided by the molecular weight of water. Since water is a molecule, we use molecular weight this time. That's 2 times the atomic mass of hydrogen plus the atomic mass of oxygen, which equals 18.02 grams per mole. So 90.0 grams divided by 18.02 grams equals 5.00 moles.
Now we can find the mole fraction, X, of NaCl. We divide the number of moles of NaCl by the total number of moles of solution we have. Our solution is 0.171 moles plus 5.00 moles, for a total of 5.17 moles. The mole fraction for HCl is 0.171 divided by 5.17 moles, which equals 0.0331. We can do the same thing to find the mole fraction for the H2O. 5.00 moles divided by 5.17 moles equals 0.967. So the mole fraction X for water is 0.967. And here you'll notice a wacky thing about mole fraction X. It's always expressed as a decimal. Go figure.
Third property, molarity.
The molarity of a solution,
represented by a capital M, is the number of moles of a solute in 1 liter of a solution. This is another way of looking at concentration in a solution. But this time, we're not looking at percentages or fractions of the whole solution. Molarity measures the amount in moles of a certain solute in 1 liter of the solution. The equation to calculate molarity is M equals N, the number of moles of solute in the solution, divided by V, the volume in liters of solution.
For example, let's find the molarity of 20 grams of sodium chloride in a 100 milliliter solution. First, as always, we have to convert from grams to moles. So using our simplified equation, we divide the mass of our sample by the formula weight of our NaCl.
So converting from grams to moles again, we have 20 grams of NaCl divided by the formula weight of NaCl, which we determined earlier is 58 grams per mole. That gives us 0.34 moles of NaCl. Now let's use the molarity formula. Molarity equals the number of moles of solute divided by the volume in liters of solution. We've got milliliters, so we need to convert to liters. 100 milliliters equals 0.100 liters, so M equals 0.34 moles divided by 0.100 liters of solution. The molarity of our solution is 3.4.
All right, heads up, because we're going to talk about molality. Now, molality sounds like molarity. It even looks like molarity, but it's not the same thing. Learn the difference so you don't screw it up on your tests. The molality of a solution, represented by small m, is the number of moles of solute per kilogram of solvent. It's the amount of solute in 1 little kilogram of solvent alone, not solution. For our NaCl example, the molality is the amount of salt in 1 kilogram of the water. See the difference? Molarity is the number of moles of solute per liter of the whole solution. So, for the NaCl example, the molarity measures the amount of NaCl in 1 liter of the whole solution. Got it? The equation for molality is lowercase m equals n, the number of moles, divided by the kilograms of solvent. So, remember to keep your m straight, and be sure to eat plenty of green, leafy vegetables.
So, the molality of a solution is the number of moles of solute per kilogram of solvent, but the molarity is the number of moles of a solute in 1 liter of solution.
Right! Care to say it once more?
Sure. The molality of a solution is the number of moles of solute per kilogram of solvent, but the molarity is the number of moles of a solute in 1 liter of solution. All right?
Okay, we're going to find the molality of a solution consisting of 10.0 grams of NaCl in 90.0 grams of water. You know what to do first. Find how many moles of solute you have. N equals 10 grams of NaCl divided by the formula weight of NaCl. The formula weight of NaCl is the sum of the masses of the atoms in NaCl's empirical formula, which comes to 58.5 grams per mole. We're taking the formula weight of NaCl to 1 decimal place further in this example than we did in the molarity example, because this time we're using 3 significant figures in our calculations. As before, we get 0.171 moles of NaCl.
Now we're ready to plug the values into the molality equation. Molality equals the number of moles of solute divided by kilograms of solvent. We have 90 grams of water, the solvent, and 90 grams equals 0.0900 kilograms. So, the molality equals 0.171 moles divided by 0.0900 kilograms. That comes to 1.90. And we have found the molality of our solution.
I would just like to say that today's college students exhibit an alarming lack of molality.
Hey man, I think I get it now. Liquids that can dissolve in each other are miscible, and liquids that can dissolve in each other are immiscible. Solubility refers to the maximum amount of a substance that you can dissolve in another particular substance. A saturated solution has accepted as much of a solute as it can. Like, it's saturated, no mas. And like mass percentage composition, mole fraction, molarity, molality, are all just different ways to describe the composition of solutions.
Section C. colligative properties.
Colligative properties are the properties of solutions that are determined by the concentration of solute and solvent molecules, or ions, present in a solution. They include freezing point depression, boiling point elevation, and osmosis.
Freezing point depression and boiling point elevation are a lot alike. They both alter the temperature at which a change of state occurs, so we can look at them together. But if you have any chemical accidents, use this eyewash station.
When solute particles interfere with a solvent's ability to freeze, that's called freezing point depression. The solute particles get in the way of the crystal formation that occurs during freezing. The freezing point depression, represented by delta T sub F, F for freezing, is proportional to the molality of the solute that's getting in the way of the freezing process. To calculate the freezing point depression, you'll use the molal freezing point depression constant, represented by K sub F. K sub F is another constant that the chemists of the past have already calculated for your ready convenience. You can look up specific K sub F for the solvent you're using in your book.
The antifreeze in your car is a solution of ethylene glycol in water. The solute, ethylene glycol, interferes with the ability of the water to form ice crystals. We figure freezing point depression with this equation. Delta T equals K sub F times M. Delta T sub F is, of course, the change in temperature, or the freezing point depression. K sub F, F for freezing, is the molal freezing point depression constant of your solvent, which you will look up in the freezing point constant table in your textbook. And lowercase m is the molality of the solution.
On the other end of the liquid temperature spectrum, a liquid boils when its vapor pressure equals the atmospheric pressure. Some solutes will cause the solution to need a higher temperature to make its vapor pressure equal the atmospheric pressure. This is called boiling point elevation. The formula for calculating boiling point elevation is delta T sub B equals K sub B times M. Look familiar?
K sub B is the molal boiling point elevation constant for your solvent. Again, you look this value up in a table in your textbook. And M is, of course, the molality of the solution. We'll figure both freezing point depression and boiling point elevation in the following example.
All right, let's talk about cars.
Automobile antifreeze is made up of ethylene glycol, C2H6O2, and water. So let's calculate both the freezing point depression and boiling point elevation of a 24.1 mass percent solution of antifreeze in water. Remember from before, mass percent is the number of grams of solute in each 100 grams of solution. So there is 24.1 grams of ethylene glycol and 100 grams of water. So starting with the freezing point, we use the equation delta T equals K sub F times M. We need to figure out the components of this equation first. Remember that little m, the molality? It equals the number of moles of solute divided by the kilograms of solvent.
So, to find the molality, we first convert grams of solute, which is 24.1 grams, to moles. Use the quick formula we gave you earlier to convert from grams to moles. That's 24.1 grams divided by the weight in grams of 1 mole of ethylene glycol, 62 grams per mole, giving us 0.389 moles of the solute ethylene glycol.
Now we can find the molality. M equals 0.389 divided by 76 grams, or 0.076 kilograms. So M, the molality, is 5.12. So now you've got molality.
Molality? What a groovy word!
We looked up K sub F, the molal freezing point depression constant for our solvent, water, and found it to be 1.86. So, the freezing point depression is that constant, 1.86, times the molality, 5.09. That gives us 9.5 degrees. Since we calculated a temperature depression, we must subtract the value, 9.5, from the usual freezing point of the solvent, water, in order to find the freezing point of the new solution. Water freezes at 0.0 degrees Celsius, so we subtract 9.5 degrees, and the new freezing point of our antifreeze and water solution is negative 9.5 degrees Celsius. The antifreeze, ethylene glycol, depress the freezing point of water by 9.5 degrees Celsius.
Now we'll find the new boiling point of the solution by figuring out the boiling point elevation in pretty much the same way. We use the same molality, 5.09, and we multiply it this time by the molar boiling point elevation constant, which we can look up for water to find that it is 0.52. This gives us a boiling point elevation of 2.6 degrees. Adding 2.6 to the boiling point of water, 100 degrees, we get 102.6 degrees Celsius for our new boiling point.
So, if you get a problem like this, you can use the same molality figures. But don't poke your eye out with the pencil in your hand. Oh!
Section D, osmosis.
Osmosis is the flow of solvent through a semi-permeable membrane from a more dilute to a more concentrated solution. A semi-permeable membrane is a divider of sorts, kind of like a sieve with very, very tiny openings that allow only some things to pass through.
Like with a sieve, the stuff that's too big to get through the pores or little holes in the membranes can't pass through. Cellophane, for example, is a man-made semi-permeable membrane because some things can pass through it and others cannot, like bacon or tuna or pork rind. Osmosis is a colligative property because it depends on the number of solute molecules or ions in the solution.
When you put a semi-permeable membrane between two solutions of different concentration and the solvent can pass through the semi-permeable membrane, osmosis will happen. The solvent in the solution of lower concentration will pass through the membrane to dilute the solution of higher concentration, in other words, to make it less concentrated, until the two solutions are more equal in concentration. Look at it this way. If the solvent is bopping back and forth through the membrane, but the solute is too big to pass through the membrane, it makes sense that the solution with more solvent and less solute will get through more quickly than the solution that had more solute that can't pass through. Eventually, the proportions will even out, so there is the same proportion of stuff that can pass through and stuff that can't pass through on each side of the membrane. When this finally happens, we say the solutions are in equilibrium.
So let's get specific. Say we have a concentrated solution of table salt, NaCl, and water on the left side of a U-shaped tube, and a dilute solution of NaCl and water on the right side of the tube. A semi-permeable membrane at the bottom of the U separates the solutions. The solute, which is the salt, is too big to pass through the membrane, but the water molecules can pass through the membrane. The more concentrated solution has more salt floating around in it, and the salt gets in the way of the water molecules' passage through the membrane. The dilute solution has less salt in the way, and water can get through the membrane more easily. So it does. Although the solvent, which is the water, is moving in both directions through the membrane, the water in the dilute solution will make its way through the membrane more quickly than the water in the concentrated solution.
So the concentrated solution is going to have more solvent flowing into it than the dilute solution will. As the solvent flows into the concentrated solution, it becomes more dilute. Eventually, there will be the same percentage of solute and solvent on each side of the membrane, and the solvent from each side will pass through the membrane at the same rate. But in order for the solution on the left to have the same concentration as the solution on the right, the solution on the left needs more solvent. So the volume of the solution on the left has increased since it now contains some of the solvent that was originally on the right.
So osmosis, does that involve the Osmonds, like Donnie and Marie? I'm a little bit country, I'm a little bit rock and roll. Those boneheads.
So freezing point depression, boiling point elevation, and osmosis are all considered colligative properties, since they depend only on the concentration of a solution, not what exactly the solution is composed of. Freezing point depression calculates how much a solute interferes with the solvent's ability to freeze. In other words, how much colder the solvent has to get before it will freeze. And boiling point elevation calculates how much a solute can interfere with the solvent's ability to boil. In other words, how much hotter the solvent has to be before it will boil. Osmosis is the movement of solvent through a semi-permeable membrane from a solution of lower concentration to a solution of higher concentration.
So now you know. You and everything around you are made up of little bundles of protons, neutrons, and electrons, which are called atoms.
You can picture the electrons zooming around the protons and neutrons in the atom's nucleus. You know how atoms stick together to form molecules and how intermolecular forces make molecules hold together to form liquids and solids.
You've got gas molecules bouncing all around you, and you know how things like space and temperature affect those gas molecules.
You know that liquid mixtures are solutions, and you know your solutes from your solvents. You can even explain to your mechanic why the antifreeze in your radiator keeps the water from freezing.
Yeah, I'd like to see you try.
And this is just the beginning. Look for more awe-inspiring video course reviews on organic chemistry, biology, physics, math, business, and more from
The Standard Deviants. Bye. Bye-bye. See ya.